In this tutorial, I will introduce equivalence rules and how we use them in proofs. Let's start with the observation that we can prove a very large number of formal proofs using only the inference rules that we've already discussed. That gives us a pretty powerful system. But there are quite a number of expressions that could be converted into the premises of one or more of the inference rules based on the fact that we know how to demonstrate logical equivalence. So let's take an example. Suppose we look at the expression, it's not the case that P and Q, and another expression, not P or not Q. Now what we have here in this expression is we have the negation of a conjunction, and in this expression we have the disjunction of two negations. So it makes a certain amount of sense that these have some sort of relationship, but let's prove what that relationship is using a truth table. So if you analyze these two expressions, we see that they have two distinct variables, P and Q. So let's set up our truth table for P and Q. Since there are two variables, that's the number of variables, we're going to need 4 rows, 1, 2, 3, 4. So we'll start with true, false, double the alternating factor, true, true, false, false. Now we're ready to start calculating values. Let's start with this expression. This is the major operator, so we'll put a little 1 there. It branches once over here because it's a unary operator. This is a level 2 operator. We have 2 branches, but both branches terminate with a variable and no more operators. So we'll start with the level 2 operator. So we'll pick up the values, as always, from the inputs, 1 row at a time, and calculate the output. So true and true makes true, false and true makes false, true and false makes false, false and false makes false. Now, taking the negation of the values that we derive for this level 2 operator, we have not true for the first line gives us false, not false gives us true, not false is true, not false is true. Okay, so we're finished with those values. Same process for the second expression. This is our level 1 operator. We have a level 2 over here and a level 2 over here. So we'll start with our level 2s. So not true is false, not false is true, not true is false, not false is true. For not Q, not true is false, not true for the second row is false, not false is true for the third, and not false is true for the fourth row. Now that we have the 2 level 2 operators calculated, we need to calculate the overall value for this expression, disjunction. So false or false gives us false, true or false gives us true, false or true gives us true, and true or true gives us true. So I'm drawing a line through the level 2 operator values we don't need anymore. So let's compare the outputs for the same inputs row by row. And what we have is on row 1 we have false, on row 2 we have true, on row 3 we have true, on row 4 we have true. So these two expressions are logically equivalent. Now let's think about what it means for expressions to be logically equivalent. Essentially, expressions that are logically equivalent can be substituted for each other either on a line by itself or as part of a larger expression in a proof without changing the truth value. That's the beauty of logical equivalence. So, for instance, let's look at a possible example here. Let's say we had on line 1 of a proof something that looked like this, not P and Q. And then on line 2 we had something like not P. And what we want to conclude is not Q. So now, let's think about this for a moment. There is no inference rule that lets us do anything with the negation of an expression in here on a line by itself. Yes, we have some negations that crop up here and there, like modus tollens, for instance, but they don't follow the schema. None of those premises follow this schema. But if we have in mind this equivalence that we just proved, and we decide to take this particular equivalence and make it an axiom in our proof system. In fact, let's give it a name. Let's name it according to the person who first discovered this property in set theory. It's called De Morgan's theorem. So De Morgan's theorem. But what we actually do is abbreviate that DN, stands for De Morgan, right? So if we embrace this as one of our axioms, then in this proof, let's go back to this. In this proof, we will be able to use De Morgan's to write what's logically equivalent to this expression on a line by itself, and that enables us to complete this particular proof. So let's do. Using De Morgan's, we can rewrite the negation of a conjunction as the disjunction of two negations. So that's going to be De Morgan applied to line 1. Now here's the thing. De Morgan, being an equivalence rule, can apply to a whole line like this or to a part of a line, but it only applies to one expression in one line, so we'll only ever see one number out beside De Morgan. It can only apply to one line at a time, right? All right, now let's analyze this expression on line 3. We have an expression here joined to another expression by a disjunction. And if we think about our inference rules, then we realize that a candidate might be disjunctive syllogism, which looks like this or that. And then we have the negation of everything in the square. And guess what? That's exactly what we have on line 2. We have the negation of the part of the first premise of disjunctive syllogism that appears in line 3. So here's the square part for disjunctive syllogism. Here's the triangle part, and here's the negation of everything in the square. So look at the form here. Even if we put not P in that square, we end up with an expression not everything in the square, which is not P. So the expression not P is exactly what we have on line 2. So on line 4, we conclude not Q by disjunctive syllogism on lines 3 and 2. Notice when we apply disjunctive syllogism, every schema matches exactly. So look, major operator of the first premise is or. That's what we have here. The major operator of the second premise is a negation sign. That's what we have here, this big negation sign out here. It's just that what's in the square happens to be an expression with a negation sign as well. At any rate, now that we have concluded not Q, the proof is complete, and we write QED.